All right. First of all, how many of you went to the quantum dealy flippy last night? All right, what did we think?
Yeah, honestly, I was looking like after the quantum thing, like, because I remember seeing like there was some quantum computing like classes, quantum theory classes, and I wanted to see if I could, you know, take it in the future. But I
Mhm.
couldn't find it on the CW website.
Well, I think there's a couple of quantum things in biology, and then we are going to be teaching a quantum class. Um, but one thing I thought he did a terrible job of doing is giving you any sort of context, like when he was talking about qubits. So he had those vectors up, the thing, like, okay, well, what the hell is this, right? So let me give you one slide that will.
You're like, I gotta fix this.
I almost did it in the moment, but I didn't want to. So you saw things, like yesterday he said a 0 is equal to, I'll write it like this. It's a like that. Actually, hold on, sorry. A 1 is a vector that looks like that. And he had them on top of each other. So it was a 1 followed by a 0. The reality here is, if I were to write this is chance of a 0 by chance of a 1. This is a 0 because there's a 100% chance of a 0 and a 0% chance of a 1. So in qubits, we represent them as vectors to give, because everything is based on probability. This is the qubit version of the 0 bit, what we talk about in computer science as being a 0 bit. 100% of the time, that will be a 0, because this is a 100% chance of a 0, and this is a 0% chance of a 1. Here's the qubit of the bit 1. 0% chance of a 0, 100% chance of a 1. A fair coin would be 0.5, 0.5. Flip a quarter, 50% chance of one side versus the other side. That would be a fair coin. That's what the qubit version of a coin flip looks like. So I'm not sure if because one of the things he really seemed to emphasize on was like, oh, how mathy it is and stuff like that. The reality is just like we're dealing with here in our, we'll call it normal computer science stuff, classical computing. You don't have to sit here and do all this calculus and stuff like that to be able to use the languages. These things are built into it. He mentioned a couple of quantum languages from IBM, Microsoft, and Google. These are programming languages that do all the scary math behind the scenes for you. So you define a qubit, you give it its probabilities. If it's a 0, because you can solve any problem that you can solve with a classical computer using qubits if you just represent all your 0s and 1s like that. You could use it as a classical computer, but then you're not gaining any of the benefits of it. So you might as well just use a classical computer is the punchline. Well, then so he talked about those programming languages, and those programming languages have gates, like he mentioned yesterday. You don't have to do the math of, hey, here's this giant matrix, and if we feed this qubit into this matrix, the Hadamard gate, it gives you this weird output thing. It doesn't matter if we can all believe the math will work, right? So if we had a programming language that said, feed this into this, and now I get this. Because really, you should view a qubit as kind of like a sphere. And inside the sphere, you have 0 is, let's say, up, 1 is down, and then we have the halvesy positions to either side, and then you have every point in the middle. So imagine being able to measure every single possible outcome inside of a sphere. That's the power of quantum, is that you can have the outcome, and really it comes down to a coin flip. If I flip a coin in the air, is that heads or tails? Still in the air. We don't know, right? Okay. That is a qubit. As soon as it lands, as soon as we measure it, Now it's an answer. That's quantum. Is that idea applied to things? And then he also didn't really give you a context for why do we say quantum? Why is it called quantum computing instead of something else? Anybody know what quantum is? When we talk about quantum, what are we talking about? If you connect the dots in what he said, if you already know the stuff and it made sense, he just skipped all the background material and then just jumped in. Quantum is how particles, how tiny subatomic particles act. So whether I'm holding a single photon here or I'm holding a cell phone, as human beings, we think we know how this object will react if I do things, right? If I drop this, we're expecting a clunk. We're expecting gravity to have an impact on it. It'll bounce a couple times. You know, we kind of know what a object with a certain mass might do, right? And if we have lighter objects, they still act the same way. They just might not have as much force or something like that. Well, when you get down to something subatomic like a photon, so this single little piece of matter, it behaves differently than a larger piece of matter. And that's the quantum world, is why do those things behave differently than things in the big boy world? But what's important is they behave consistently. They behave differently, but they behave consistently. The coolest experiment of this is something called the double slit experiment. It will keep you up at night. So the idea is you have a let's say you have a flashlight, okay, and then we put a piece of we're by a wall here, so we put a piece of cardboard up between us and the wall, so it's blocking us, and we cut two little slits into the cardboard. All right, now we're going to flash the flashlight on this thing, and then we're going to look at what gets through on the wall. All right, now you might expect that you would just get like two little dots on the wall, you know, where the slits were, right? That isn't actually what you get. You get something called an interference pattern, where you have a whole bunch of like waves on the wall. Like, even though the wall is only behind these slits in two places, you get light all over the wall in like this weird pattern. Fine, that's interesting, whatever. And maybe you've even heard this. They reference this on like the Big Bang Theory show. Said, oh, particles act like waves instead of particles, or light acts like a wave instead of a particle. If it was a particle, it would just be two dots on the wall. Since it's a wave, it's the whole thing. And you can imagine this like in a swimming pool. If you did that same thing in a swimming pool and you pushed water at it, the water would come flowing through, and then it would still have a ripple effect after the fact, right? All right, that's what it looks like. Now, so it was like, okay, we'll just accept that. Well, let's go and do just in case, since we're firing so many light photons at this, why don't we build a machine that only fires a single photon and see what happens on the other side? Certainly a single photon is just going to give us the one dot. It doesn't. The single photon gives you the same interference pattern. All right, okay, fine. I guess that's interesting, but like I said, it's consistent. All right, so we're following this thing so far. Okay, nothing keeping you up at night yet, just, oh, it acts like a wave instead of a particle. We're going to have that exact same setup, but we're going to change one thing. They're saying, oh, well, I wonder what's happening to those particles as they pass through the slits. So they set up a camera and observe it. Just look at it. They change nothing else other than look at it. Now they act like particles. No longer is it a wave on the wall. Now it's two dots. The only thing they change is they looked at it. Kind of like, you got caught with your hand in the cookie jar. So in some ways, it's like almost like kind of proof of an intelligent design. It's like, okay, it acts one way when nobody's looking, but it acts another way when somebody is looking. It's creepy.
So because you put a
Camera, human eye, doesn't matter. If you measure it in any way, without touching it, you don't have to manipulate it at all. If you measure it at all, and this is quantum computing is based on this, the quantum state does what's called collapses. and then you get your answer. Coin's up in the air. It's in a spin state. It's flipping. It could be anything. Let's say it's a wave. As soon as it lands and we measure it, we got our answer. Well, now we're seeing it in real time, watching these subatomic particles behave differently, whether when we're looking versus when we're not looking, with no other change. I mean, isn't that creepy? And if you just do a search online, like on YouTube, for double slit experiment, there's all sorts of like cartoon depictions of what I just described. And then, you know, some people said, well, certainly there's something funny. So there's expanded experiments where they try to force it to behave a different. Now it keeps failing. Every single time you peek, it behaves differently. Which,
you can repeat it.
oh, 100%. Yeah, it's completely repeatable, completely consistent. Bottom line is subatomic particles act one way when you're not looking, act a different way when you are, even if you're not touching them. Yeah. Where this cell phone is going to act the same way when I look at it or when I don't look at it, right? Okay, like it's not like dancing around and stuff. I stopped looking at it, but it's behaving the same way as it was when I turned to look at it. It didn't just change. Okay, photons would not do that. Photons change when you look at it. We don't know. So that's what's kind of, I know, fun and scary about quantum computing is because it's consistent, we can do operations using it, but we don't understand why it works that way.
Nothing is more scary in science when the answer is we have no idea.
Yep.
We don't know.
You know, and then he also used the word, go ahead. Do you have a question? Yeah, that's actually, that was about what I was going to bring up. He kept using the word entanglement, but he never defined the word entanglement. Entanglement is kind of related to what I just said. If I have two different smartphones, same smartphone, but two physically different copies, two instances of the smartphone, keeping it connected to our objects we're doing in class right now, right? Okay. If I crack the screen on one of them, nothing happens to the other one, right? Okay. Pass by value. we had a copy of it, right? All right. Same thing's true if I have two photons and, you know, I do something to one of the photons, nothing happens to the other photon, right? That would, if all photons were what's called entangled, and you do something to one, it happens to all the other ones, light on Earth would kind of suck, right? But we have a mechanism by which we can entangle these things, and entangling particles is very difficult. And that's kind of why we don't have quantum computers with more qubits in them, because it's hard to create entangled particles. All right, but let's just assume that we have an entangled particle. So if this cell phone was an entangled particle, we're just kind of building it up to a bigger size, and I crack the screen on one. Is this thing doing the flicker thing? Quantum. Yeah. If these guys were entangled, if I crack the screen on one, the same thing will happen to the other, even though I didn't touch it. All right. Now entanglement has so you might say, okay, whatever. Again, that's interesting, but how can we use that? Well, then we add to that and say, by the way, this entanglement thing happens at any distance. So I could be sitting right here and I can shatter the screen on this other one and that one shatters in front of you. Or we can move this one to the top of the Eiffel Tower and I can sit here and shatter it and that one will still shatter. Or, and he mentioned this, the Chinese used a laser to put a particle on the moon, an entangled particle on the moon, and made a change to the particle here and measured it there, and the change had occurred there. Okay. No connection. Yeah, the connection is quantum entanglement. Somehow they're linked. And we can manipulate particles. I don't know the exact process, but effectively creating entangled particles is possible, but it's difficult. That's why we don't have quantum computers with 1,000,000 qubits in them, because qubits, we have a certain number of entangled qubits inside of a quantum computer. So making them in bulk is difficult. That's why we don't have them. And he did mention that the quantum computers that we have today have a relatively few number of qubits. There's a company selling a physical quantum computer for consumers that has 2 qubits in it, which is an interesting thing for experimenting with qubits, but you can't solve real problems with that. He did mention the thing called the traveling salesman problem, where the idea, there's a classification of problems dealing with real computers. So we'll call these classical, quantum people call them classical computers, but this is a computer to us, right? There is a class of problems called order NP problems, where this guy has a lot of trouble dealing with those kinds of problems. It takes them thousands of years, blah, 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 to do even the simplest thing. And a really simple example of this is reducing fractions. So if you have a fraction with let's call it a giant numerator and a giant denominator, and you want to reduce that fraction, you want to find the greatest common divisor of the numerator and the denominator. Yeah, that doesn't seem like a big deal, right? Well, you just start at 1. You start at maybe the smaller of the 2 numbers, right? And you start counting down until you find a number that divides both of them evenly. Yeah, it's just modulus, right? Looking for a remainder of 0. Seems pretty straightforward, right? Not a big deal. It is a big deal computationally, because the number of numbers we have to test for really large numerators and denominators is astronomical, right? If you have a 600-digit number in the numerator and the denominator, you have to count through a lot of digits, and that's going to take forever. I rounded down. Okay. So and we actually have an algorithm called the Euclidean algorithm that allows us to do that much quicker. It allows us to take giant skips through those things to give us the greatest common divisor. And there's a program that we can write in class. It's not a real difficult program that either tries to do the brute force version of reducing a fraction or uses the Euclidean algorithm to do it. And Euclidean algorithm is like 5 lines of code. It's not like a really crazy thing. It's just a math trick. There's just a math trick in it. If you just did a search for Euclidean algorithm, there's pseudocode out there that's, it's 5 lines of code. It's nothing major. It just utilizes some math principle to keep cutting it down to jump to the answer more quickly, instead of bazillion. It's a real number, by the way. Things you have to test. You can do it in like maybe 100,000 or something like that. So that's a type of problem that is computationally difficult for a classical computer. Or that type of problem on a quantum computer, it can, with enough qubits to represent the number, you can collapse it down instantaneously, because those spheres, those qubit spheres, they can hold every single possible outcome. And then as soon as you observe it, it collapses to the greatest common divisor, if you program it the right way, something like that. So it can hold a massive amount of data inside of these things that on the surface don't necessarily seem that much more complicated than a normal bit, a 0 or 1, but they're actually far, far, far more complicated, and they rely on science that we don't understand. Just kind of a interesting thing. So the traveling salesman problem is one of those problems. And the idea is you have the salesman who, has to travel to, 10 different cities on his route on a given day. Maybe he starts here in Mequon and he has to go to Grafton, Port Washington, Milwaukee, Waukesha, blah, 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 And each one of those cities has a distance. There's these roads that connect all these places, and there's different routes you can take to get to Waukesha from here, for example. Well, the idea is so the question that we're trying to answer is, what is the most efficient way for this guy to do his job? To start in Mequon, end up in Mequon, and visit every city that he's supposed to visit while being as optimal as possible in terms of time or miles, depending how you want to measure it, doesn't matter. That's another kind of problem that is very difficult for classical computers. So we have approximation algorithms like one's called Dijkstra's algorithm that he mentioned yesterday. That is the, you know, a common solution to that problem, but it's still something called divide and conquer, where you are you're literally trying every single possible thing, but you are cutting out paths along the way that you just know are going to fail. So it's an optimization, but it's a crappy optimization. Dijkstra's algorithm makes it doable on this kind of computer, but for very large maps, it becomes, untenable. But probably in our example of Wisconsin, we could probably use Dijkstra's algorithm, and a normal classical computer can pull it off. Those are the kinds of problems that a quantum computer can solve better than a classical computer. So it's not an upgrade to the computer sitting in front of you. It's a new way of solving problems where certain problems lend themselves to quantum solutions.
So it's not just like a fast.
No,
It's just
absolutely not.
It's just a completely different way of solving problems.
Correct. And in fact, the idea would be we can solve any classical problem on a quantum computer, but you would almost view that, so I'm trying to connect some of the stuff to what we talk about in here. You can almost view that as an interpreted language, where you're going through this middleman to do something that you could have done natively before. So you really probably lose speed doing problems in a classical way on a quantum computer just because you can. It's not faster just by any sort of definition. All right. But the punchline here is that entangled qubits are difficult to create. And he talked about some of the different quantum computer technologies that these different companies are using. They're effectively messing around with different kinds of particles to see, are some of these easier to entangle than others? That's what the manufacturing process is, what's currently evolving for building quantum computers, because constructing qubits is expensive, difficult, all those things. And that's why we don't have a computer with zillions of qubits yet. So it becomes just this fascinating thing. But what's exciting and scary about quantum all at the same time is it is trustworthy. So we know exactly what the outcome will be. We just don't know why it behaves that way. So we can use it to solve problems, even though effectively we're using this black box where we're feeding things into it, and then we're observing the result, and we're just happy with it being the right answer, without paying a whole lot of attention to why did God make it work this way? that type of thing. It's kind of an interesting thing. But where this is going to impact normal consumers the most initially, and he did reference this, but like I said, he maybe did a poor job of connecting some of the dots, is with a lot of our security. So for instance, when you go to a website, you're putting your credit card in, you get the little padlock on the bottom of the site. What does that tell you? It tells you you're safe, right? You don't know how you're safe. They're doing something to make you safe. All right. Well, that's going to use an encryption algorithm of some kind. And most of our modern encryption algorithms, he mentioned one called RSA, but they're based on a mathematical principle that doesn't seem like it would be that difficult, just like that reducing fractions problem doesn't, but it actually is computationally difficult, where it takes something like 3 trillion years to crack your credit card code. You might get it on the first try, but on average, it takes something like 3 trillion years. And that principle is, if we take two big prime numbers, if you take two small prime numbers, and you multiply them together, and you say, well, tell me which prime numbers were multiplied together to get you this. For instance, let's take the number 15. So it's like 3 times 5 gives us 15. 3 is prime, 5 is prime. If I gave you the number 15, I said 2 prime numbers were multiplied together to give you 15, you could probably figure that out, right? Well, now let's take 2 gigantic prime numbers, multiply those guys together, and say what 2 prime numbers were multiplied together to give us this number. The security of being able to factor 2 large primes out of a product is computationally ridiculously expensive. That's the kind of problem that quantum would be very, 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 very good at. So all of a sudden, those 3 trillion years turns into something more like 5 minutes. Well, that kind of collapses our entire digital security
Everything's
world.
vulnerable.
Yeah, everything's vulnerable. So some of the first research being done in quantum deals with quantum encryption algorithms. So basically, new encryption algorithms that have defenses against quantum while still also being strong against classical. So we kind of have a new enemy, if you will, with the quantum computers. There, I think that's last night's talk in a nutshell. But maybe hopefully in a little bit clearer. And the thing is, it's not that he didn't talk about the stuff. He just didn't give you the context for where it was coming from. He just threw matrices up and like, let's do math. And then he kept saying, I'm not going to get into the math. He just kept showing you math. Oh, but well, I guess one last thing. He did mention the programming languages that are out there. So Microsoft has one called Q#, which the syntax is C#, which all of you already know because you know C++. And C# is very similar to C++. But effectively, these quantum languages, they look like a normal programming language. They just have functions that let you mimic the different quantum gates that he referenced. So you can write programs today that take advantage. You can instantiate a couple of qubit objects. So there's an object type in there called a qubit. You can instantiate a couple of those, and then you can pass that qubit through these different gates and get your result and yada, 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 and see all that. But because we don't have big enough physical quantum computers behind the scenes, the quantum programming languages right now are emulated, which means you can get the functional correct result, but you're not getting the benefit of the speed. So if you go and use one of these quantum programming languages today to solve the traveling salesman problem thing, you can do that and for a proof of correctness, like, oh, this works. This algorithm that I've written in quantum works, but you're not going to get the blistering speed that I'm promising because it's being run on a classical computer that's emulating what this gate does to this qubit. Because the math works out. We understand what this gate does to this qubit and what the outcome will be. But we're not benefiting from that happening inside of the physics of quantum mechanics on a real quantum computer. So we're not gaining all the speed. We're running it on a bicycle, which is still interesting from an academic perspective, because now, even today, we can write quantum programs and quantum solutions to problems. We just can't run larger ones on a physical quantum computer. So you're not getting the actual speed performance. It'll still take 3 trillion years. It's because you're just abstracting this crack the RSA code thing. You know, you've written it in quantum stuff, but it's running on this computer, which is still going to suck at doing those things in bulk. So that's the world we're living in today. But the big warning from the talk was Google has claimed that they're going to hit what's called quantum dominance by the end of the year, and they very well might. And that's building, you know, if you look at the evolution of these quantum computers, it starts off with like, you know, 1 qubit, 6 qubits, 24 qubits. You know, before long, we're going to have 1 million qubits. And once you have, I don't remember what the exact number for quantum dominance is for that says it can solve general classifications of problems. Whatever enough qubits is to do that, we're getting close, is the punchline. For multi-billion-dollar quantum computers, not sitting on your desk at home, but somebody will, IBM, Google, Microsoft, although Microsoft I don't think builds quantum machines. They might, but definitely Google and IBM do. IBM is probably the big boy. There's actually a quantum computer in Chicago that IBM created. I don't remember how many qubits are in there. It's impressive, but not quantum dominance yet. And they look really cool. They look kind of like chandeliers. Like, that's not a computer. No, I don't know. Quantum is really cool, but it's more scary. And for us as computer scientists to appreciate what our world is likely going to look like from a job perspective 5 or 10 years from now. The chances of you dealing with something involving quantum, even as short as 5 years from now, is pretty high. Just because quantum is going to throw a wrench in a lot of our security solutions and things like that. And then once people start solving those, we're going to look at, oh, how can we apply quantum to all these other things? You know, very similar to, if we just switch things, very similar to like the blockchain type stuff. You know, blockchain being, you know, how many of you have heard of blockchain? Okay, 1.5 people. How many of you have heard of Bitcoin? All of you heard it. Bitcoin is the name of a token that exists to make blockchain work. There is a blockchain called the Bitcoin blockchain, and there's a math algorithm that makes that blockchain work. And the necessary production of that math problem, the necessary output of that math problem is a token called Bitcoin. On that one, there's an Ethereum blockchain, there's a there's a Ripple block, there's a zillion different blockchains. There's a Dogecoin blockchain, if any of you have gotten involved in that. But in any case, blockchain is also going to be something that's becoming already today. There's tons and tons of jobs dealing with blockchain, and it's going to become more and more prevalent now that it seems like we're rounding the corner from people viewing blockchain technology as investment stuff. Like, people buy and sell Bitcoins to make money, right? That seems to be that's not the power of blockchain. Sure, maybe some point in the future we might decide that we want to replace regular money with some sort of digital money. All the sci-fi books do it, right? What's usually called credits. How many credits do you have? Something like that. Okay. But really, we're already doing that, right? I mean, most of us don't really carry around that much paper and metal currency with us. We have a credit card or Apple Pay or whatever. You know, all your money, you log into some website, you see a number on the screen. That's your bank account. You never saw those dollars. You don't have like a safe in the back with a stack of cash, right? We're already digital. We're just trusting, you know, your bank or whatever to keep it safe. And all your banks are FDIC insured up to $150,000. Isn't that good? That means if your bank gets robbed, as long as you have, each of your accounts has less than $150,000 in it, the government will replace your money. That's good, right? We like that. Well, how many of you would be willing to give that up just so you didn't have to trust the government? It's like, I'll just keep it in this guy's shed. You know, he's going to stand outside and guard it for me. And whenever I need my money, I'll go back and get it. But if somebody sweeps in and steals my money, it's gone. Will we like that? You didn't have to trust the government, though. Yeah, see, human beings are greedy. We want our cake and we want to eat it too. You know, the best example is usually something like Amazon. Most of us have shopped on Amazon before, right? Now, Amazon, a pretty rich company. Yeah, made a lot of money, blah, blah, blah. Just making money off of you, right? Even though you perceive you're getting the best deals on Amazon, right? All right. So now, how many of you would trust that if you bought something on Amazon and you sent them the money for it in an envelope, cash in an envelope, that Amazon would likely send you the product?
That's how you did that.
Yeah, but they probably would, right? We've established a level of trust in Amazon. We might not like them. We might think they're mean and rich and all this stuff, but we trust that there's been enough positive transactions with Amazon that it would be in their best interest to take our $50 in cash arriving by envelope and still send us the real product. We trust that would probably happen, right? And that's because we're trusting a known entity, Amazon, okay, which we might think is evil, but we trust them nonetheless.
I want my controller here in 2 days.
Yeah. Right. Well, the whole world of crypto breaks all that. Now you're going to send somebody your, 4 Ethereum to buy something. And then they don't send it. Let's say they receive the 4 Ethereum, it's in their crypto wallet, and then they never send you the item. Could that happen? It certainly could happen. It could happen with Amazon, but you trust that it wouldn't. Well, what do you do if you send somebody 4 Ethereum and they don't send you the product? Who do you call? Ghostbusters, right? Okay. There's nobody to complain to. Gone. At that point, you're just relying on human ethics that, oh, humans certainly wouldn't cheat other humans. Whew, that's not going to last real long at all, will it? Yeah, we don't like that. That's why we like PayPal. When you buy stuff and you pay for it with PayPal, PayPal protects you. They have a system where you can say, hey, look, I sent this money. They never sent me the thing. PayPal will open an investigation. If that person can't prove a shipment tracking, whatever, blah, 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 they refund the money. We like that, but we don't like trusting people. We want both. We want to not have to trust anybody, but we also want all our stuff and to be protected. And we don't get both sides. So
Is that the fundamental problem with crypto?
100%.
You could just get scammed if there's nothing.
Correct. Nobody to complain to. Nobody to complain to.
Yeah, kind of like how what was covered in that other talk that had those, where's it, where, yeah, I think I kind of making point that was basically the Wild West.
Well, almost even worse. Because at least in the Wild West, you can go and chase down the dude and his horse.
You can go to the sheriff.
You don't even know who's taking your crypto money. And I think where this is hopefully most important, I'm sitting here arguing that crypto and things like that are not replacements for currencies. Yeah, I'm somebody who has profited wildly off of crypto. I've been into crypto for years. I taught a course here in 2008 on Bitcoin. And yeah, it's up on my YouTube channel. It's still in a 4:3 aspect ratio. And we wrote we were using blockchain to write a voting system. And back then, the only cool blockchain was Bitcoin. By today's standards, as we were testing our program, we were transacting hundreds of thousands of dollars during class, because you could see my Bitcoin wallet on there. At one point in time, I had something like 5 million Bitcoin. I still maintained quite a bit of Bitcoin and sold at a pretty high. I sold at around 79,000. So I did okay. And some of you know that I work here for health insurance. So so it's
My dad was, I knew someone that got in the Bitcoin. He's like, I should have. I'm like, you would never. It's okay.
yeah, but early on it was cool. You can mine Bitcoin with your normal computer.
It takes energy, right? That's what.
Yeah. But in the early days, nobody was doing it, so you could just use your normal processor to do it. Well, then once enough people started playing, then you had to use your graphics card, and then they started building these specialized things called application-specific integrated circuits, ASICs, and then they kept building faster and faster and faster and faster ASICs. It took more and more energy. Well, all of a sudden, the only people who could afford to do it were like the big investment banks and stuff, and they're the only ones mining the crypto. Now, if you wanted to sit there and mine these coins, you could play a little tiny role and maybe make some money, but you wouldn't make zillions unless crypto jumped, did something stupid. Ethereum's a good example. Ethereum existed to be what's called ASIC resistant. So there were no specialized machines that could be built to mine Ethereum. So Ethereum was mined with graphics cards in normal people's computer. And whether you were a PC gamer with a single good graphics card, and whenever you weren't playing your games, you wanted to mine Ethereum, or you were the professional Ethereum miner, the only difference between you two were he had more graphics cards. You were still using the same equipment to do it. So you played your percentage role, blah, blah, blah. It's not our future currency. It might be our future currency, but we like to trust people. We just like to complain about the people we trust.
So we can use it, but we'll give them this.
Well, but there's some practical uses. So now we're rounding the corner with practical uses of blockchain. For instance, the one of the blockchains that I'm a big fan of is something called Ripple. The symbol is XRP. And it's a for-profit company, so there is somebody to scream at if something goes wrong. But Ripple solves a real problem that's we have here at the university. It solves the problem of bank-to-bank transfers. If you want to send money from your bank here to your bank back home in Minnesota, let's say, no big deal, right? Because American bank systems are compatible with each other. Okay. What if you're a Indian student who's come over here from India, and back home your currency is rupees, and here our currency is US dollars, right? And you want to send money back to India. How do you do it? Current way of doing it is you go through some shady guy on the internet who will do the transfer for you, and he might steal your crap. Okay. What Ripple does is it connects disconnected banking systems, because you can use your normal bank to send money from the United States to India. It just takes like 2 weeks and has a lot of fees associated with it. Same thing with sending money to China or any other country that has a non-US banking system. So what Ripple does is Ripple basically creates a gateway. Think of it like an airplane. So you take 100,000 US dollars, you turn it into Ripple, you send it over the Ripple network, which takes less than 3 seconds. It arrives at its destination wallet, maybe the bank in India, who transfers it immediately to rupees. The only possible fluctuation in value was how much Ripple changed in value over those 3 seconds, let's say. So the network was used as transport only, secure transport of the money. It represented your value for just a moment, but then in the end, you still held it in what's called fiat currency, rupees, US dollars, whatever it is. That's a legitimate use of blockchain. Not to sit there and hold 4 zillion Ripple because you think it's going to increase in value. It might increase in value because, I mean, there's only so many Ripple that were ever created. There's 10 billion Ripple that were created. And the more the Ripple network gets used, the more each of those Ripple will be worth, because they have to represent larger dollar amounts. So somebody who invests in Ripple, that's the only crypto that I currently have. Well, I have that, and I have Stellar Lumens, which is like an open source version of Ripple that isn't owned by a for-profit company, but is geared towards solving the same problems. But there's your crypto lecture.
It's nice to hear like some actually trying to do like buy into it now. You do it right now. Now you're like, no.
Well, and hopefully it carries some water, because like I said, I did okay with Bitcoin. I think maybe my cash out was something $78 million, something like that.
78
million. Yeah, a couple of Bitcoin. But I'm sitting here telling you it's a bad investment. Right time, right place, right? Anybody can get lucky.
Yeah.
You know, I think I've told the story with, yeah, well, yeah, I think I've told you, at least some of you have heard my story of when I wrote software for Apple App Store. I had 4 applications that were out the day it came out. And one of them was a dice roller that made $3 million. If I released that app today, it would make a nickel, if I'm lucky. Okay, but on day 1 of the App Store, everybody bought every app. Just, oh, apps are great. Let's check them out. It's $1. It's $1.99. Yeah. So right time, right place. That's the
opportunity.
Yeah. All right. So we covered quantum, we covered blockchain. Now we need to cover this keyword, right? See how simple this is going to be after just talking about all that stuff? Oh, you had a question, didn't you?
Yeah. With Ethereum, I know with the GPU, the market was ridiculous, like back in the code and stuff like that.
Yeah.
Did it change from like being GPU dominant? Because I know they all.
It's now, they used to use proof of work, which means you had to have a piece of equipment to mine it, like GPUs. Now they switch the Ethereum blockchain to use something called proof of stake.
Is it the 2.0 that came up?
Yeah. And you could think of proof of stake kind of like when you're a member of a board and you have so much stock in a company, the more Ethereum you hold, the more votes you get. So as long as one person doesn't hold more than 51% of the all Ethereum that exists, which they don't currently there, because there's this thing called the 51% problem in any crypto. But as long as one person doesn't hold more than 51%, you can validate transactions just based on the number of crypto that a zillion different people have. They cast their votes saying, yes, this is good, and they're not having to use tons of electricity to do it. Yeah. Because
you still mine it at all or no?
No, it's not mineable anymore. Yeah. And that's what, well, you can mine other crypto, or you can mine Ethereum 1.0. Because what they did is they did a hard fork on the the blockchain. So that old blockchain still exists. Yeah, it just doesn't have real value because everybody's adopted the 2.0 version of it. But the statistic there, I mentioned the application specific integrated circuits with Bitcoin is the amount of electricity it takes. It's probably more than this now, but this is probably a 3-year-old fact. The amount of electricity it takes to manage the Bitcoin network on a daily basis is the same amount of power it takes to power Argentina. Well, the amount of electricity these people are spending mining Bitcoin, competing with each other because Bitcoin is the reward they get for validating transactions. Just like we use Visa, when you swipe your credit card and Visa takes their 2%, that's the reward they get. And what are we doing? Businesses and people are trusting Visa to validate those transactions. And we're okay with that. We trust Visa. Visa's making bank off of us. They're making bank off these off the businesses, just so the businesses make it more convenient for us to buy crap. We love it. Yeah, but now we're saying, oh, well, we don't want to trust Visa. We want to have zillions of people all pretending to be Visa, and they all have to agree with each other, at least having a majority over 51% on what the current state of everybody's wallet is. You know, what transactions have happened in Bitcoins in the last 10 minutes. And that is the new state of the blockchain. When we could just trust Visa. And that's fine.
It just becomes done.
And maybe, you know, we fast forward 50 years, maybe some kind of crazy calamity might happen and we don't trust anybody, or, you know, life as we know it has changed. And all of a sudden this whole proof of stake thing, you know, might work. And it's effectively the digital version of the barter system, where you're going from village to village, you know, trading your animal skins for bread. You have what you have and somebody else wants that and you trade it, and it's the digital barter system. Fascinating world. All right. So last time when we were talking about objects, we introduced and the context of this, I think I probably have an example of this in here. Do I have it in my dice? Yeah. So part of the need for this starts with this guy. So for my dice object here, I've said that dice is going to manage a single field, a number of sides. Okay. And I'm going to name that variable sides. And then I have my constructor. Constructors are kind of method like, they look like methods, but they don't have return types. And these guys, their job is to initially construct the object, initialize the object. To build a new dice object, I have to tell it how many sides. Well, for this guy, I'm going to take in a variable. Instead of calling it sides, which makes plenty of sense, I'm going to artificially make sure its name is unique to this guy's name. Which I'm going to say is bad programming, but it's what we've had to do now because we haven't learned about this keyword yet. So I've named this guy number of sides. So that inside the implementation of the constructor, I'm setting sides equal to number of sides. And all variables resolve to their most local definition. The variable sides, what does that resolve to? Well, we look locally. Is there a variable up here named sides? Nope. Is there a variable up here named sides? Nope. So we'll jump up one level and, oh, we see that the class actually owns a variable called sides. So the first place I see a variable named sides is the class's field. Go ahead. It is, but it all lives inside of the dice class. We can think of the dice class here as our global environment. Well, we've seen it before where we created a variable up here. Right. Well, if you do it inside of main here, what you're talking about is if I define a variable here, and then down here, I have another function int do something. I don't have access to this variable called something down here. Yeah, because the scope of this variable lives and dies with main. This is a whole brand new scope. But if I were to put int something up here, now I could access it. Because this is a global variable. We had talked about that. Remember, I said that kind of the rule of thumb is that global variables are bad. And I adjusted that and say global variables are usually bad or something like that. It's not that they don't have a place, but they're easy to abuse. Because if you don't understand scoping rules, you don't understand that, oh, things I define in main are only accessible in main. Things I define in do something are only accessible in do something. You might just say, well, if I don't really understand that and my program's not working, I'll just move the variable global here. And oh, it magically starts working. This must be right. Well, it works because you basically just threw everything up in the cloud, so you have access to it everywhere, which is great. It's convenient, but I'll tell you what, as soon as your program gets reasonably big, you're going to wish you didn't put all your variables in one gigantic bucket. Okay, because we're dealing with very small problems here. Even though I know that you feel like, yeah, well, I'm spending a lot of time on my assignments, blah, blah, blah. These are tiny, tiny, tiny problems. If we opened up the source code for Microsoft Windows or something, you're going to see crap you understand. You're going to see ints in there. You're going to see for loops, if statements, all the same junk. You're just going to see millions and millions and millions of lines of it. All right, yeah. So this comes back. This comes down to variable scope. Who has access to what? So the rules haven't changed with objects. It's the same deal. So here, when I say sides, I'm setting some variable. This is the assignment operator. The single equal sign is the assignment operator. I'm setting the variable on the left-hand side equal to the value on the right-hand side. Well, I need to figure out, well, where am I going to put this new value? Well, I'm putting it wherever sides is. So I look around locally. I don't find it there. I look in my parameter list. I don't find it there. Then I look to my one last place. The one last place I can look at here that we know of is the fields of this class. And we find sides there. So I'm setting that variable sides equal to number of sides. And what's number of sides? Again, all variables resolve to their most local definition. So first I look around the floor. I don't find it there. Then I look in my parameter list. Number of sides is right there. So it is this value that I'm setting equal to this value. But the way I'm accomplishing that is I'm playing the game of artificially making sure those variables have unique names. When really I might say, you know what? The number of sides that a dice object has, it makes sense to just call that sides. And if I'm going to call it sides there, why shouldn't I call it sides there? And why shouldn't I call it like that? But this creates our problem. Because now I'm going to say, oh, again, all variables resolve to their most local definition. Sides, I look around the floor, don't see it. I look at my parameter list. It's right there. We never get to this version of sides, because he was what's called shadowed by this more local version of sides. All variables resolve to their most local definition. So right now I'm setting this guy equal to himself. Oh, go ahead, then I'll come to you. No error. Just isn't what you want it to do. Yeah, when I declared the second version of sides here, this is a more local version of that variable called sides, and it does what's called shadows the more global variable. And what I mean by shadows is it supports that idea of variables resolved to their most local definition. So when I say sides here, it finds this version of it, not this more global version of it, but it's not an error. Just currently, I'm not doing what I intend to do. I intend to set this guy equal to this guy. That's what I want to have happen. But what I've currently written here is I've set this guy equal to himself. Good.
I was gonna say so that, I was making sure I understand this correctly. So that, like local is like this right next to, and then that one, I think it's like far away.
Yeah, so we might say on the floor, that's what I've been saying here. And then this guy is the parameters. And then this guy is the, call it global fields. So when from the perspective of this constructor, the first place I'll look for variables is on the floor around me. Variables that were defined inside of this guy. Now, to add to it, I can't do that. It will not let me define another variable called sides here when one was passed in. It would say there's already a variable in this scope named sides. So I'm kind of artificially talking about on the floor and the parameters as two separate things, but they both belong to the actual same scope. So this would not be allowed, and this would give you an error if you did that. All right. But the way I like to look at it is the first thing I do is I look at, have I defined any variables before this line of code that might fulfill the guy I'm talking about? Or let's then check my local parameter list. Or if that none of that works, my last stop is I can look at the fields that were defined by this guy. It makes sense? All right. So in our line of code right here, we know what we want to say, but what we've actually said isn't what we want to say. And this is the common problem that intermediate programmers start running into. We know enough to be dangerous, and sometimes we believe what we've written is what we meant to write, but it doesn't mean what we think it means, right? And this is going to be part of your entire career. I mean, you see me do it in here where I'm like, okay, well, how does this language treat a certain thing? And you just write a couple of lines of code to experiment with it until you see, oh, it behaves this way in this language. Sometimes you just need to do that. But this is a pretty consistent thing. Scoping rules are universal among programming languages. This is how variable scope works, regardless of what language you're in. All right. So I need to have a way of setting this version of sides equal to this version of sides. And we do that using the this keyword. The this keyword is how an object refers to itself inside of itself. Okay, so if we pretend like I'm a freshly, well, actually, we're making it too weird. Okay, we're in the middle of being born. Okay, yeah. As part of the birthing process, the constructor is called, right? So right now I'm in the middle of this constructor being called. So, but I'm already a thing. All right. So I'm an instance, I'm an instance in process of a dice object. And what I really want to do is I want to set the number of sides that I know about equal to the number of sides that my constructor was sent. So I need to have some way of talking about my variables, the fields that I own. Okay. And we do that using the this keyword. So I'm saying set the sides variable that is owned by me. That bypasses the floor, bypasses the parameters, and goes right to the fields that belong to me. Set my value of sides equal to whatever that is, which then follows the rules of variables resolved to their most local definitions. I look on the floor, don't find it. I look in the parameters right there. So now I'm setting my version of sides. You can also think of this as kind of like the full, given the full path to something. I'm telling you exactly which version of sides that I want you to set don't follow normal scoping rules. Don't look on the floor, then in the parameters. I'm telling you, you can find it with my stuff, with this is stuff, because this is how I refer to myself. The this keyword is kind of like how a human being says I or my. Okay. So I'm setting my version of sides equal to that value of sides, which resolves to this version of sides. That makes some sense?
Global, and then global equals to the one.
Yeah, but I would really, as we're learning about the this keyword, because this is specific to object-oriented programming. Other languages like Python, instead of the word this, they use the word self. So those are probably your two most common ways of referring to your own things from the perspective of an instance of an object. This and self. You could probably split the languages down the middle, and it's one of those two. I think I mentioned that an older language, Visual Basic, it used a keyword called my, which I actually kind of like. It never took off, but that starts feeling more human. Maybe self is better than this in that case, because self is like, oh, this is the stuff that belongs to myself. Makes more sense than just this random word this. But we're starting with one of the early popular object-oriented languages, C++, and they use the keyword this. So all of our C++ based languages use this. They just kept it around. All right. Yeah. And I don't think it makes no sense.
Yeah.
But I would not translate this guy automatically to talk about global. It effectively is that, but as we get deeper into object-oriented programming, we're going to start talking about something. This will be next semester. We'll talk about something called a singleton, where we can actually create something even more global. You know, and if you want to think about it with maybe something you already have a context for, what if you have a database in the cloud? We have other places to ask than just floor, parameters, and right above. But right now, in the world that we live in, those are our three places to check, following the scoping rules that we've already looked. And really, 98% of the time, when you're writing code for your entire career, it's going to be those three places you're looking. Go ahead.
So with this keyword, it's going straight to the object, and it's not like skipping the first instance that it finds as it works its way out.
It's going directly to the fields owned by this object. Really, I would say it's going directly to the members owned by this object, because you can use this keyword to also call other methods, not just fields. But yeah, it's going to the things owned by the current instance, this instance that's being born. Where this is how a particular instance of an object refers to itself from inside of itself. When I'm talking about inside my head, I might say, I am going to the zoo. You know, where it's weird to other people, I say, Mike's going to the zoo. We make fun of people when they do that, but you know, people do it, right? So talking in the third person thing. Okay. But when I'm thinking about things in terms of me saying, you know, if I say Mike's going to the zoo, and one of you say you're going to the zoo, then we're both instances of human, but we're different instances. So when I say I have a nickname for Mike, because that's my name, right? And each of you has a name. So you can kind of use a shorthand and talk about yourself, okay? But what if there's two Mikes in the room? Mike's going to the zoo. Well, which Mike? There's no confusing when you say I am going to the zoo. Everybody in here knows that we're talking about me, okay? None of you get to come to the zoo. I only have one ticket, and it's elephant ride day. One of the few animals I can ride. They get real uncomfortable when you start trying to, you know, like ride the baby giraffes and stuff. Although they're shockingly strong. Giraffes are crazy strong. Well, yeah, when they do the neck fighting, but there's also videos of like, you know, because lions will like hunt giraffes in packs, and a single kick from a giraffe, it causes a lion to expire. Quick. Go ahead. That is what this keyword does. That's the magic.
How do you know it refers to that?
Because how do you know when I say I am going to the zoo, I'm talking about myself and not that he's going to the zoo?
Well,
Same thing is true here. If I'm a dice object in the process of being born and I start talking about this, I'm talking about myself. I'm talking about I'm saying I want to set my version of that sides variable. Okay, the variable called sides, that's one of my fields. I want to set that equal to the sides that the constructor got passed to it.
on the original constructor.
Well, this is the constructor. Yeah. This is just me implementing it. You know, we're still looking at the splitting into two files thing where I have my kind of my documentation. This is what a dice object is. He owns these variables, these fields. He has this constructor and he has a single method called roll. Now, and like I mentioned a second ago, I can also do something like this. I can say, I would probably do it after I seed my random number generator. I could also use this to call my roll method. What's the difference between these two lines? Go ahead.
Isn't there no difference at all?
Correct. No difference at all. Functionally, these guys work the same, but not for some new concept. It's scoping rules. I know that this guy's a method because I see the opening close parentheses, right? That's the kind of animal he is. He's a method. I know this guy's a variable because I don't see opening closing parentheses. So not a variable. All right. Or he is a variable, not a method. So when I just say roll like this, I'm going to check in the places that I have access to. I'm going to check in the scopes around me to decide where is roll. Well, we're not allowed to define methods inside of methods. So we're not going to, well, it's a half lie. You can't define named methods inside of methods. Forget you heard that, but it's a thing. Okay. They're called closures is the kind of animal I just described. You can have a method defined inside of a method, but not with a name. It has to be used in real time. We'll see that a couple classes from now, like courses from now. Okay, but you can't define methods inside of methods. So I'm really wasting my time looking around on the floor. Okay, you can't define methods inside of parameter lists unless there are closures. Okay, so I'm wasting my time looking at the parameters. So my last place to look is inside of the class, which here's my roll method. So the first place I find a roll method is the one owned by the class anyways. And the reality here is that's the only place I'm actually going to look because of where I'm allowed to define methods. But I like to always use this keyword for this, where I'm saying, call the roll method owned by me, my version of the roll method. Okay, anybody know why I think this line is preferable over this line? Even though, as he pointed out, they effectively do the same thing.
More efficient. You don't have to like search through multiple scopes.
It might be more efficient. I would argue in this case, because of where you're allowed to define methods, it probably is not more efficient because the first place you'll look is the place you'll find it. Go ahead.
Does it have to do with you define a variable in where you're calling the function that would same as one that's global?
No. Go ahead.
Could be readability more, but I mean, because if you call it roll one of the files.
Possibly readability. That's a reasonable answer. I would say that's still not the answer of why I do it. It's maybe related to the answer that I do. So that line of thinking is along the lines of what I'm getting at here. Does anybody else want to take a guess along those lines? It's not an efficiency. It's not a computation thing. It's a spelling thing. Right now, we're writing our code, and I don't think it does it in here, does it? But if I just say roll, it does it too. If I were doing this in a integrated development environment, some special text editor built for programmers. So maybe it's Android Studio, maybe it's Eclipse for Java, Visual Studio for C# code, some effectively word processor for programmers. One of the things that those things typically have today, they have auto indentation stuff. We've seen that in here, but they also have command completion. So now I don't really have an excuse to shorthand the name of variables and methods. I can have the name of those guys be descriptive as to what they mean. Because when I say this dot, it would give me a list of the things to choose from. And I would choose the role from that list, and it would go ahead and autofill it in for me, which would remove the possibility of me having a typo. Make sense? So it's really me leveraging the programming tools that a professional developer would typically use to reduce the number of stupid mistakes. I'm far, far, far more likely to have typos in my code than logic errors. I've been doing this long enough that it's not that common that I'll think that something means one thing when it actually meant something else. But it's very common that I misspell stuff. But whenever I do, I did it on purpose to see if you can catch debugging errors as they're happening. Plus, I have bad tremors on my left hand, so you never know where that thumb's going to jump. True story. That's bad. I'm relying on it getting a lot worse because I can go on disability. So I need my hands to type, right? So at this point, it's just drastically impacting my putting in golf. Yeah, it's pretty bad. Just sitting there shaking over the. Plus, it's very noticeable in VR because they're tracked so well. And as I'm in VR, because you can see this hand shaking, and it gets way worse than that. It's like when I have a cup and I start getting it. Isn't that messed up? I'm always dumping food on myself. It doesn't hurt at all. It's just a thing. And it's not Parkinson's. They've looked at it. I keep seeing. No, I keep seeing neurologists, and they just call it an essential tremor, which is equivalent to they don't know.
Oh.
It's the quantum computing. And then they say, you know what, we can give you pills for it, but the side effects of the pills are way worse than the tremor. I'm like, well, unless they're recreational, which, don't do drugs.
Yeah. Ban drugs, don't drop out of school.
Yeah, all that stuff. But yeah, so I'm prone to typos, let's say, and many of us are, right? Even, you might be I'm a pretty accurate typer, but I'm prone to typos. So if I can leverage the tool I'm using to have less typos by just choosing to use this keyword, which also maybe makes my code more readable, makes it more obvious, and potentially makes it more optimized. In this case, it certainly didn't hurt, right? Well, might as well take advantage of it. All right. Questions about this? Okay. Do we understand what this keyword is used for?
Yeah.
All right. So now, and I think I'd mentioned this either last class or the class before that, that concept is something that I would say most professional developers do not understand. They can't explain it to you why it works. Instead, they've come up with the, this is just what you have to do. If you want to name your variables like this, you just have to use this keyword. It's how it works. Something like that. Now, you could still make a good living with that kind of mentality and stuff like that, but I would argue that to be a good computer scientist, you should never just take a correct solution and run with it, minus a super important deadline or something, where you just say, I'll figure this out later, but this works. Okay, but in general, we should be inquisitive and be like, okay, obviously I was doing something wrong before, this works now, why? And then start doing some experiments to figure out why does this function the way it's going to function. All right, so what we're going to look at starting next time, and we're running out of classes, but if you go online and you do a search for something called a MUD, I'm guessing many of you, well, here, let me just go images real quick. These are multi-user dungeons. So think about games like World of Warcraft and things like that before we had graphics in our computers. Okay. So something like this where we have like a description of the room we're in. You know, here's our number of hit points, spell points, here's our stamina. And then it's asking us to type in a command where, you know, it also probably shows us where the obvious exits are. We see we have a huge minotaur in this room. There's another player in the room. Usually there's some obvious exits where you can say, I'm going to go north or west or east. So we're going to start building a map of rooms with exits and a player, and have our player be able to walk through this map of rooms. And maybe we'll put a monster in there to kill, which goes back to our death match. Remember all that? All right. So we're going to play around with objects, and that hopefully sounds a little bit complicated, but rooms are pretty simple. They have descriptions. They have a collection of who's in the room, and then they have exits, collection of exits. So we'll try to wrap some of those things up. And then what we're going to do is we're going to start next semester, 250 class, off with reproducing our starting point of this in Java so that we can pretty quickly introduce multi-threaded programming. Because we're going to notice pretty quickly that, oh, how do I make my my world, my dungeon here, how do I make it alive? Or maybe a rat wanders into the room, that kind of stuff, where you maybe have something occur like every second or something like that. Questions, comments, concerns, bribes?
Every time I see one of those, I always think of use torch. You don't have torch. Use hand. I do not have to do it for it. Darn it. It's the only thing about it.
So
Just to make sure, except for the